Okay, some seismology for a change. So the topic today is going to be tomography and anisotropy. These are basically there's going to be two parts, and I kind of wasn't quite sure in which order I would do this, but because there's not really that much time to cover everything, so I decided I would start with a very basic introduction to seismic anisotropy, building upon what we've already heard in previous lectures, and really not digging into the details, and then spend the rest of the lecture on tomography, which is going to be primarily isotropic tomography. So, in an anisotropic structure, seismic waves propagate with different velocities in different directions. And here there's already a typo. Seismic waves propagate in different directions. We've already seen that the main causes of anisotropy can be either shape-preferred orientation, like if you have layering, or crystal-preferred orientation, also called lattice-preferred orientation, which is related to microscopic fabric. In the Earth, we find anisotropy, seismic anisotropy, primarily in the crust and the upper mantle. And much of it is related to the deformation of olivine, whose crystal is anisotropic, in the lowermost mantle, the D double prime region, and in the inner core, the iron coming from the anisotropy of iron crystals. I'm not going to be talking about the inner core. Whatever I'm going to be saying is mostly applies to the mantle. So as we've seen in Ved's talk and some of the mineral physics talk, in an isotropic medium, we have Hooke's law, which is written with relating the stress tensor to the strain tensor, and with two parameters, lambda and mu. And here I'm using the notation with the contraction of the indices and the chronicle delta symbol. And so here, we can define this relationship either using the shear modulus and the compressional modulus, or the Lamé parameters lambda and mu with a relationship between them, or we can introduce the velocities of the seismic waves, the P wave velocity and the S wave velocity, shear wave velocity, which relate to the other parameters like this, introducing this additional parameter of density. So now in an anisotropic medium, in the more general, which is the more general case, the relationship, as we've already seen, is more general, with relating the two second-order tensors through a fourth-order tensor, which is the elastic tensor. And we've seen that originally this tensor has 81 elements, but there can be only up to 21 independent elements of this elastic tensor. And the number of independent elements is related to symmetries in the system. And so if we think in terms of crystal symmetries, we've seen some of similar plots. We can have different numbers of independent elements. The simplest one following isotropy is the cubic system, and the ones we're most interested in, that we most frequently encounter in the upper mantle, would be the orthorhombic system, which is that of olivine with 9 independent quantities, 3 planes of symmetry, and the hexagonal. Very frequently, we actually approximate olivine with a hexagonal system, even though it is really orthorhombic. The hexagonal system has an axis of symmetry.
That may be confusing for people going from how do you? So oftentimes we talk about like bulk parameters that are only valid for an isotropic system, and so I think it might be worthwhile to explain how you get from crystals with different symmetries to isotropic parameters. Would that be?
I think we've covered that with the Voigt averaging and Royce averaging. Didn't somebody talk about this?
No, we didn't.
I wasn't prepared to show anything about this, but you can you can, either average it by, sort of adding the strains or adding the stresses, right? And you get two different averages, which is the Voigt and the Royce, right? And I guess mineral physicists, seismologists don't really go into that kind of detail, but mineral physicists get an average which could be somewhere in between those two, right? Is that a fair explanation?
It bears pointing out that Voigt-Royce average, which is then you add the name Hill to it to say that you're averaging it, isn't actually based on physics. So there's not a direct physical basis for it. It seems to work. And so that's something to just be aware of, is that when you're trying to average out these different elastic properties, that we're kind of, we're doing a good job, but it's not directly based on physics. And so there's places where that approach is going to break down. The two limits are based on physics, yeah.
But they give different results, so that's the issue.
Extraordinarily different results. They're not close, and you're averaging two numbers that are close to each other. They're very, very different, and they're based on the assumption of constant stress and the assumption of constant strain.
I thought, Greg, what you're talking about, isn't it that not averaging several different types of phases, but it's the fact that this is for one crystal. There are lots of crystals, and they're in all different angles,
It's
and
going
that's why you
from
get
one crystal to a multi.
Averaging.
So skip
polycrystal.
We kind of skipped a little bit there, but I think most of what your comment was that the way you end up with olivine behaving more or less isotropically is you have a whole bunch of different olivine crystals with random orientation.
Right. Okay. So just the other question you might have is, how do we go from the elastic tensor to actually velocities? And this is done through, you can show that there is a relationship which gives you the velocity of propagation of a seismic wave in a particular direction, defined by the normal direction to the wavefront. So a particular seismic wave will be defined by its polarization. And so you solve this equation, basically, which is called the Christopher equation, where you have two vectors, right? The wave's polarization vector and the direction of propagation. And so you can compute, knowing the wave's polarization direction and the direction of propagation, you can compute its velocity for a given elastic tensor. Okay, and you solve it by solving this system, which is an eigenvalue problem. Okay, so right, there are three eigenvalues which give three velocities: a p velocity and two s velocities. So simple. Of course, we have to simplify things in seismology because we're not going to be able to resolve the 21 elements of the elastic tensor. So simplest system, which we use a lot and which we can resolve in some cases, is the case of radial anisotropy, also called vertical transverse isotropy. It's a hexagonal symmetry case, and one example is layering. If you have layers of material with different properties, you're going to have a different velocity going in this direction, and if the waves propagate in this direction. And so depending on your direction of propagation, you will, we will need to describe the velocities in this direction, in this direction of propagation, in this direction of propagation, and in intermediate directions of propagation. And in this case, it turns out this can be described with 5 independent elements of the elastic tensor, which were named by Love in 1911 as ACFLN, and we use this notation very much. Some of these can be related directly to the velocities of particular waves. So L is related to the velocity of propagation of a shear wave that is vertically polarized. N is a shear wave related to the velocity of a shear wave horizontally polarized, same for PV and pH, and this fifth parameter, F or eta, describes some properties in directions of intermediate directions. There is a need for radial anisotropy in the Earth, and that's expressed very well in the 1D reference PREM model. In order to, it comes from, this need comes from trying to find a model that will fit both the dispersion of Rayleigh waves and love waves. So Rayleigh waves, which are primarily sensitive to SV, and love waves, which are primarily sensitive to SH. In order to reconcile them in a single model, you need to introduce radial anisotropy, or VTI, and this is especially strong in the uppermost mantle, the upper 200 kilometers of the mantle, where on average VSH is faster than VSV. And so this is what's expressed in this model, which has this somewhat artificial discontinuity at 220 kilometers, which reflects the fact that this anisotropy is actually strongest in this shallow part, but also that so this connects to an isotropic model below 220 kilometers. There's also evidence, but not globally, but in some regions, that there is actually might be a discontinuity at about this depth, but it's not global. Okay, so
just a quick question. Just to understand, how much is the fact that we have our strongest observed anisotropy in the upper layers due to the fact we can observe it using Love and Rayleigh waves? Do we expect a similar sort of anisotropy lower as well, or is that just a...
Well, you don't need it, basically, at least on average.
Okay.
On average, you don't need it. There is, okay. It's harder to detect because it's smaller, and actually in the lower mantle, it's probably not even needed. You need it once you get to the deep lowermost mantle. But for the surface waves, it's absolutely required. Yeah.
And I just wanted to add to that. It's not just, I mean, you made it sound like we put in the top because the surface waves require it, and that's the only place the surface waves are sensitive. Body waves, of course, are also very sensitive to anisotropy as well, and you can see it in SKS splitting and things like that. And to first order, you can see similar signals from SKS splitting as you can see from, say, upgoing S splitting, which means that you don't need a lot in most of the mid part of the mantle.
One more question?
Can't cross the aisle. It's against the rules.
Do you want to comment on the possibility that in 1D models, apparent radial anisotropy is really azimuthal anisotropy bleeding into an azimuthally averaged model?
Well, okay, you have to be careful about this, and I'm going to talk about azimuthal anisotropy in a minute. However, at the 1D model level, I think this is pretty robust. That is, we are careful to average over many azimuths when these measurements are made. So I think whereas there is a little bit of possible bleeding, you basically need to average very well over azimuths to get a robust measurement of the part that's symmetric. I don't think this is a problem at the 1D level. When you go to 3D, when you start looking at lateral variations in anisotropy, this becomes more of an issue. This is only a reference model, by the way, okay? This is not necessarily physically meaningful. Okay. Yes, one more.
Can you comment on the presence of strong anisotropy at the bottom of the lithosphere in PREM? So the strongest anisotropy in PREM is at the shallowest parts of the upper mantle, right? And then it decreases up till as you go to 220.
I think this is pretty. I think this is a pretty good kind of reflection of the average, observations. Okay. Remember, this is just 1D. Do you want to say something? Okay. So, as I said, radial anisotropy is observed very strongly and needs to be introduced to reconcile love and Rayleigh wave observations. So in this case, the assumption is a vertical axis of symmetry, and so you should have these 5 independent parameters, right, of the elastic tensor. In fact, surface waves are not, we cannot resolve all of these, and they're primarily sensitive to shear wave, and they're primarily sensitive to the 2 parameters L and N, therefore, the SV and SH polarized velocities. So what we really can resolve is only 2 of these parameters. I put this in italics because in 1D we can resolve this parameter eta to some extent, but it's very difficult to actually resolve it independently in 3D. So typically you will this is what you're going to be seeing is a description of the model either in L and N or equivalently in terms of something that we call the isotropic velocity, which is defined like this as the Voigt averaging, and this parameter which expresses the anisotropy, so the difference between the velocities of SH and SV polarized waves. Okay, and if you look at variations, relative variations of this is expressed as the difference between the relative variations of the SH and the SV waves. Okay, and this should be an index here, of course. Okay, so this is an example from a paper by Lebedev and collaborators showing, how this difference between SH and SV velocities is reflected in the modeling. These are actually this slide is made to show that models are not non-unique, but what it shows is models, 2 possible models of one, velocity versus depth for a particular path in the Baltic Shield between 2 stations located in the Baltic Shield. The data are in blue. The data are marked by the black lines here, which express some the uncertainty in the data. And the predictions from these 2 models are the red for love waves and the blue for Rayleigh waves. And the point of this slide is so that you can see that you always have SH faster than SV to match these data, but you can match them equally well. I mean, you obtain predictions that are practically identical using slightly different constraints on how you build your model. This one allows a sort of a low velocity zone here in the around 50 kilometers depth. This one doesn't. Okay. What you need to be aware of is that extracting an isotropic signal, even this one parameter xi, right, VSH over VSV squared, is more difficult than extracting the isotropic part of the velocity, because the sensitivity of the waves is still lower than for isotropic velocities. These are kernels. I mean, we introduced kernels in previous lectures, so it's the sensitivity of particular waves. Here, this is a fundamental mode Rayleigh wave, and this is a first overtone Rayleigh wave, and this is the depth dependence of the kernels, so the sensitivity to depth, to structure at different depths of this Rayleigh wave at 2 different periods, 60 seconds and 100 seconds. And you can see the only point of showing this slide is that here, this is the sensitivity to xi, and you can see it's about only up to 20% of the sensitivity to Vs. This is for the first overtone. What you see here, the first overtone is sensitive to greater depths at the same period. So it's one illustration why it's useful to have overtone data if you want to study structure at larger depths. But it's also, here 0.4 and here not quite minus 0.1. The kernel for xi is much smaller than the one for for the isotropic part.
But these are love waves?
Are they love waves?
I
Maybe.
think so,
Yeah.
but
I said really?
Well, I don't know if you said. I was just trying to.
Could be. I don't know. I don't remember. They could be love waves. They look like love waves because yes, you're probably right. Okay.
What?
We'll check.
Okay.
Doesn't matter. The point is, it would be the same if it's love wave or radio waves. Okay, so this was for radial anisotropy. So olivine crystals, of course, are anisotropic. And if you take just one crystal, you will see very large differences between the different axes. Of course, if the orientation of individual crystals is random, then the rock may appear isotropic. This is what some of the discussion we had already addressed. If you have a deformation process, like shearing in a mantle flow, then some of the crystals will align with the flow, not completely, but they will, align in a particular direction. So this will generate seismic anisotropy. Obviously, the seismic anisotropy that you will get, the strength of the seismic anisotropy that we'll get will be much lower than the anisotropy of a single crystal, because all the crystals are never going to be completely aligned. Okay. We have evidence for this kind of anisotropy dating back to this early paper of Hess in 1964, who looked at the distribution with azimuths, that is, distribution with the direction of observation of waves which are called PN waves, which are P-type waves that propagate right at the MOHO. So looking at the difference in velocity of these waves, whether as a function of azimuth, okay? And basically seeing this regular pattern, this sinusoidal pattern in 2 psi, where if psi is the azimuth, with the maximum in the spreading direction. And this fits well with an interpretation in terms of alignment of olivine crystals in the flow. And so the relationship, I should say, though, that the relationship between the actual alignment of olivine crystals and the flow is not, and how you relate the flow to anisotropy in the seismic system is not perfect, but it is, and it all depends whether you are purely solid or if you have some water, etc., because this, the slip system change depending on these conditions. But to first order, it's not such a bad approximation to say that, the observation of this kind of azimuthal variations can tell you something about the direction of flow. Yes?
One more comment, though. That's for P waves, right? Where
yes.
The fast and the slowest correspond to the crystallographic axis. But you showed in the previous plot where you showed the olivine for S, that's actually not corresponding to the crystallographic axis, right?
Right.
So it's oblique to the axis.
Yes. So there are other complications.
Right.
Yes. So anyway, going back to seismology, so we saw radial anisotropy and how that's important to introduce in analyzing seismic data. So the azimuthal variations can be captured in this dependence of the velocity on the direction propagation in the horizontal plane. So you can think of it very naturally for surface waves, which kind of propagate along the surface of the Earth. You can also think of it very naturally for waves that propagate vertically in vertical paths, right? So, but in any case, otherwise you have to project things onto the horizontal plane. But to first order, it can be shown that the velocity of waves in any model, of any anisotropic model, can be expressed in terms of an expression like this, which depends on 2 psi and 4 psi, where psi is the azimuth, which can be typically counted counterclockwise from north. And all these coefficients are linear combinations of the elastic tensor coefficients. And in fact, to this first order, there's only 13 terms that come in place. So A will contain your radial anisotropy, your azimuth-independent part. So it will be a function of ACFLN. And then B, C, which are the tube side terms, are combinations of 6 different elements of the elastic tensor, and D and E are a combination of two other elastic elements. So there's 13, and so you may ask what happened to the other 8. Well, the other 8 come in the odd terms, so you would have a cosine psi, sine psi, and cosine 3 psi, and sine 3 psi, but they do not, to first order, they can be ignored, okay, which is helpful. So in practice, only as I said already, 2 radial anisotropy terms, L and N, can really be resolved up to now. And then 2 of the tube side terms can be resolved if you think in terms of upper mantle structure, which are called GC and GS. This is just a convention. And this GC multiplies the cosine 2 psi, and GS multiplies the sine 2 psi. So from that, you can define an amplitude, G, and a direction, psi f, which is the direction of the fast axis. And so, and the other terms, the other 4 terms, are usually scaled to these terms. They are scaled using some kind of assumptions on the mineral compositions, or there's been some experiments to measure these dependencies, and they may or may not be correct. But the sensitivity of the waves to these terms have to be included in the fact that you have to use this scaling, but you can't really resolve them from the inversion. Okay, so basically from seismic data, and this is surface waves, but I'm going to bring up some other types of data too in a minute, you can resolve basically LN and GCGS. That's essentially the bottom line. This is an example of tomography map where surface waves azimuthal anisotropy was inverted for. So this shows a 60-second period dispersion of Rayleigh waves. In the background is the isotropic velocity variations. There's no scale, but this is VS isotropic. Red is negative, is slower than average. Blue is faster than average. And on top of it are represented these bars, whose direction is direction of the fast axis and whose amplitude is proportional to the amplitude of this G term. And so typically there's no scale again here, but this would be like maybe about 2%, I would say, these bars. And you can see from this figure, you can see some relationship already, like here near the specific rise, you see these bars are more or less trending perpendicular to the ridge. Then in this relatively young ocean, they are trending in the direction of absolute plate motion. And then as you get into the older part of the plate, you lose this. Remember, 60-second period, you're sensitive to a particular depth range. And this can be interpreted as in this part here, you're sensitive to the asthenosphere because the lithosphere is very thin. But as you go to older ages, what you're seeing is a signal coming from the lithosphere. So the other type of waves that are used most commonly to study anisotropy is shear wave splitting, and very specifically SKS splitting. So if you have a shear wave that is coming from an isotropic medium and traversing an anisotropic medium, it will split into 2 S waves, right? And these two waves will be polarized differently and will travel at different speeds. So when you get out of this anisotropic medium, and back into an isotropic medium, you will continue to have two waves that will be shifted in time, one from the other. And that time shift will be related to a combination of how long you spent in this anisotropic medium and the strength of anisotropy. Okay, the trade-off between the two.
Is it really the case that there is some conversion happening in this anisotropic medium, or is it rather the case that there were like both modes were present in the isotropic part and then just split up because of the different velocities in this medium? So is there some kind of energy loss due to conversion in this anisotropic medium?
I don't think you lose energy. This is purely elastic.
So in principle, both of these waves were present before and just split up because of different velocities.
Yeah, okay. So now I'm going to explain what SKS is.
It depends on the orientation of the polarization of the original wave, even if it's a single polarization, relative to the anisotropy axes of the anisotropic layer. You might only excite one of those modes if you happen to come in parallel to the fast direction, or you might only excite the other mode. If you're in between, they're both already present.
Just one small detail, you're talking about loss of energy. I mean, this will look like, it can look like a contrast in elastic property, so you can get transmission and reflection as well. So, but you're not losing energy, you're just, okay.
Okay, so the most convenient, of course, the most convenient, it so happens that the Earth is such that it provides some ways of that are kind of really convenient for us to study anisotropy in the upper mantle. And for this, we use the SKS wave, which is a shear wave starting from the source through the mantle, then it converts to a P wave, and then it converts back to an S wave. Why is this useful? I mean, we want to know where the anisotropy is. I mean, we may observe splitting, actually. This is here. I'll explain this in a minute. But, okay, so this shear wave could be polarized in any way, in any way here from the source to the core. But as it is converted to a P wave, when it comes out and gets converted to an S wave, it converts to an SV wave, a pure SV wave, because you can't produce SH from P. Okay, so at least you know that whatever observation of anisotropy you observe here at the top must have been originating in this part of the path. Okay, so that doesn't mean necessarily that it originates in the upper mantle. However, if you have observations coming from many different directions at a given station, and if they are coherent in the way that you have the dependence of azimuth, then it is most likely that the anisotropy originates in the part of the path where all these waves are sampling the same region, which is the upper mantle, where they are practically vertical. Okay, it's also, of course, helped by the fact that there is not much observation of shear wave anisotropy in the lower mantle, so we don't have to worry about that part of the mantle too much. There is anisotropy at the base of the mantle, but the SKS wave spends very little time in that region, and again, we by averaging over many different azimuths, this will produce maybe some jitter in your fitting of your azimuthal variations, but on average, the kind of coherent signal will come from the part of the path which is the same for all the waves. Okay, so this is one of the kind of very powerful observations of anisotropy, besides the law of Rayleigh wave discrepancy. Now for body waves, is that if the material was isotropic, you would expect to see the SKS wave only on the radial component of the you have three components of the observations. You have vertical, and then you have two horizontals. One, originally it would be two seismometers, one north and one east, but you can always rotate them to the one that's in the direction of your propagation, so in the plane that contains the source and the receiver, the vertical plane that contains the source and the receiver, and the orthogonal plane. If the wave is SV polarized, you will not see any signal on the transverse component. So you should see only SKS only on this component. But we very frequently see it also on the transverse component. This wave is slightly delayed from this one. And it also has slightly different frequency content. And all of this kind of fits theoretically very well with the idea, with the presence of anisotropy. Okay, the particle motion that you can get from this for this wave will be elliptical rather than linear. Okay, I didn't want to get into too much detail on this. And so, so people do measurements of SKS splitting. They represent it also as little bars, giving the direction of fastest propagation direction, and amplitude proportional to the strength or the splitting time, the delay between the two waves, the one that's observed. Well, you have to decompose it then into the fast and the slow wave, so it would be the delay time between the fast and the slow wave, and that gives you a measure of the strength of anisotropy if you assume some thickness over which this happens. And this is just an example over North America, which is already old, with the US array network that has been marching across North America. The data are now very, filling out these gaps. But you can see that there is, in general, consistency across large regions with some variations, which then you can map into upper mantle structure. Okay, so this was just a brief introduction. Why do we care? Well, why do we care? Well, we care because if we have these quantities, if we can measure these quantities, so the isotropic velocity or its variations with respect to a reference model or a 1D model, the radial anisotropy, also expressed in terms of its variations, and also the azimuthal anisotropy, in a very, very simplistic cartoon way, you can have access to a lot of information about the Earth. And so this is just a cartoon showing what would happen in a very simple convection cell, where you have an upwelling here, some horizontal flow, and then a downwelling here. In this case, you expect the velocities to be lower in the upwelling part because it's hotter, and faster in the downwelling part because it's colder, and sort of neutral in the middle. So this is this. The radial anisotropy, on the other hand, will give you different picture. Both the upwellings and the downwellings will appear as SV faster than SH, and the horizontal part of the cell will appear as SH faster than SV. So already with this correspondence, you might have some better idea of the geometry of the flow. And then the azimuthal anisotropy can give you the orientation of this cell in space, right? Because this is just a 2D cell. You can, with the azimuth, you can orient this cell in space. Okay, so this is very simple. So this was just a very brief introduction to anisotropy. I see it raised more questions than it answered, but I will transition to the other part, which is really mantle tomography. And most of what I'm going to be talking about is really the isotropic tomography. I might get to the talk about anisotropy a little bit if there is time. So you already have some idea of how mantle tomography works. You did the, at least from the inverse theory point of view. So I will not go back to describe the equations and all these issues of trade-offs between, and resolution. This is just, to remind you what we do is we we map seismic waves, mostly at the global scale. We will have maps of shear velocity. There are also some compressional velocity models. What we actually map or image are velocities, right? Slow and fast. And we like to translate that. I mean, the users of this will want to interpret this in terms of temperature and variations in composition. To first order, the temperature effects may be larger, so we transition very quickly to this interpretation in terms of temperature, but the caution is that, in fact, velocities depend not only on temperature, but also on composition. So this is just, the color scale is kind of inspired by this idea. So just one slide to kind of explain in words how tomography works, because it's an opportunity to make a few points. So if you have a homogeneous body, right, you have a reference model in which you know how to compute everything. You know the velocity, so it's a homogeneous, let's say VP here, a single number for all this body. You know the shape of the body. You put some sources on the surface and some receivers at the other end. In this particular case, the waves will travel along straight path, so you know also the path of the waves. And so you can compute the travel time of this wave, knowing the velocity and the length of the path exactly, right? So you know exactly what you're measuring, and you know exactly what you're computing. Now, suppose that in fact there are some hidden inhomogeneities in this body, which is what you want to try and find. And so if you have one observations from this source S2 here to this station B, this is a faster than average body, and this is a slower than average body. You measure the travel time here. You're going to measure a travel time that's going to be shorter, right? This wave is going to be arriving a little sooner than it would be in your reference model. So this gives you an idea that there's something that's speeding up the wave going here. If you have a path that goes through the slow wave, it's the opposite. You're going to get a travel time that's going to be slower than in the reference model. So this is, if you only have one, right, one of each, you can say, oh, I have some inhomogeneities that are faster than average and slower than average, but there's no way you can really constrain where they are, right? If you only have this one, your inhomogeneities could be anywhere. But if you add a number of other paths like this one, which is normal, now you can separate the space into a slow and a fast part. And if you add many other paths, you will be able to constrain more precisely which region is affected by the fast velocity and which by the slow velocity. And so the point here is that you need many crossing paths in many directions in order to be able to constrain both the shape and the strength of the different anomalies, right? And so that's sort of a hand-waving way of describing how tomography works. Of course, you put this into equations which you already kind of seen in a way. So what do we need to do tomography? We need first a reference model, a model in which we know how to calculate exactly the quantities that we want to measure. Typically, it would be travel times of some waves. And we know how to, in that reference model also, we know the paths, etc. That's the first thing. Typically, you would want to choose it as close as possible to your real Earth, right? And the Earth is good to us in the sense that the 1D Earth, that is, it wouldn't be homogeneous in the case of the Earth. It would be a 1D structure depending only on depth, but that the differences between our reference model and the actual Earth are small, right? You need to parameterize physically, right? We need to know what these travel times are going to be depending on. So in this case, it will be just the VP velocity, the P velocity, but it could be a number of other parameters. You did a theoretical relationship, travel times equal length divided by VP in this case. And you need then, if you want to compute this, not by hand waving, but formally put this in the computer, you need to parameterize your system, and for example in blocks, right? And once you have your block parameterization, you're able and you know your paths, and to first order, because of Fermat's principle, as Ved explained to us, these paths are known. You can compute the portion of length of the path in each block. You have your velocity or reference velocity in each of these blocks, which need not be the same everywhere. And therefore, you can compute what the travel time or the travel time difference between your observed wave and your reference wave as a function of these different velocities in all these blocks and the length of paths. And then this is an integral over the ray path gamma, which can be transformed into a discrete sum. And there you form this is your anomaly, so your model M, and your matrix G, which relates your model to your observed travel times. And so you form this problem, which is what Mark Spanning's lecture was all about. Okay. So what do we use for tomography in seismology? The easiest, of course, is the measurement of a P waves. Because the P waves, or the P wave travel times, the P waves are the first that arrive when there is an earthquake. So before the arrival of the P wave, if you have a quiet station, there is no signal, right? So you can actually accurately measure the arrival time of the P wave. You can, with some slightly more difficulties, but you can also measure the arrival time of the S wave generally quite well, because both these waves are well separated in the seismogram. The P wave in particular also is a relatively high frequency wave, so this theoretical assumption that the travel time depends only on the geometrical ray path, which is an infinite frequency approximation, is relatively a good approximation for the P wave. So that's why historically, tomography has really gotten off the ground with measurements of P wave travel times and then S wave travel times. These are the data that are the waves sample the mantle quite well. Well, I'll show you the problems, but and these measurements are easy to make. For surface waves, of course, we also measure travel times of surface waves. When we measure dispersion, we measure the travel time as a function of frequency. That has been discussed previously. And so the fundamental mode surface waves, which are well separated also on the seismogram, you can measure their dispersion also relatively using relatively simple methods. So these are the two types of waves that are the most commonly used. And however, there are some issues. So for talking about the body waves, we have a limited distribution of sources, right, around the plate boundaries for the most part, and we also have a limited distribution of stations because they're mostly on the continental masses, right? There are some islands, but islands are noisy, and especially in the southern hemisphere, we don't have very good coverage. And that is reflected. This is an old slide, but it still kind of makes the point. You can kind of look at how you sample your volume, which is, of course, one of the very, very important things, is how you sample your volume so that you can separate different heterogeneities in different locations. This is showing for P waves, for P wave travel time tomography, the difference in sampling. This is at the top of the lower mantle, and this is at the base of the lower mantle. And you see how non-uniform it is. I mean, it kind of makes sense, right? Because we don't have earthquakes or stations in the middle of the ocean basins and fewer in the southern hemisphere. Coverage is really rather poor in the middle of the oceans. On the other hand, it's quite good in the around the subduction zones, because in the subduction zones you have both a lot of sources and also a lot of stations in the continent, so you can illuminate your structures from many different directions, which is the condition for getting good model. Yes?
Question: how common practice is it, and how much of a difference does it make to propagate the rays through the reference model versus propagating them through the perturbed final model?
It makes it might make some difference, but it's there are other things that are more important, which is finite frequency effects, which is related, really. But I think I'm not sure this is correct to say, but most studies will stick with the initial model. Depends whether you're doing it at the global scale or the regional scale. For regional scale models, people have become more sophisticated and they iterate their ray paths. For global scale models, I think this is rarely done. Okay. And by the time you get to the lowermost mantle, you see the coverage is more or less uniform, but it's actually not that good. Okay. And so P-wave tomography is really very powerful in subduction zones. That's really the point I want to make. In fact, in the next slide, I'm showing two cases that are where P-wave tomography, velocity tomography at the global scale has been used, or we would want to use it, so to image slabs and to image plumes. But I will show you a few more slides of slabs. In the case of slabs, we really have a very good coverage. In the case of plumes, there are problems because these plumes happen to, these hotspots from which these plumes allegedly originate are in the middle of the ocean where there are very few earthquakes and stations. So in fact, you are prone to smearing along the ray path, right? So when you look at a picture like this, you will have the question, is this really a continuous structure, or is the continuous structure just an artifact of the fact that you don't have many crossing rays? And so there's been a lot of debates about this particular model of Montelli ever since they published this model. I will give you some more details on this maybe later. So, of course, you can do checkerboards, and we know that checkerboards are not perfect. Checkerboard tests we've heard about from Mark, and I think you did that in the tutorial also. They only reflect some aspect of the model construction. They do not address the theory, and they do not necessarily address actual structures, but they give you some indication of your sampling at least. So this is from Carson and Van der Hilst 2000, showing in the lower mantle, how much you can recover over the checkerboard using actually a combination of P-wave, speed diffract, and PKP. And here you have initially, right, the input checkerboard is filled, right? The whole global model is filled. And what you get out, you can see, is quite well recovered in the northern hemispheric continents, here at the 1,000 kilometers, 2,000 kilometers. By the time you get to the core mantle boundary, they switch to larger checkerboard patterns because of the loss of resolution. But you can see that in all cases, basically the southern hemisphere is really not very well sampled, and even the northern part of the Pacific Ocean. If you add, here the point made here is this is only using P waves, so only waves that bottom in the mantle but don't reach the core mantle boundary. This is adding some other types of waves, diffracted waves on the core mantle boundary, which allow you to sample more of the core mantle boundary, and PKP waves, which are waves that go into the core. And there is some improvement. This is a difference between these two checkerboards. So in this region, you get some slight improvement, but it's not that great. Yes?
Maybe it's a little naive question, but how... So it looks like, we have in the southern hemisphere and maybe under Africa, we don't have very good resolution in general.
Well, for P waves.
For P waves. Okay, so with other.
Yes, so that's what I'm going to talk about later. Yes.
Well, I was going to say, are there any places in the Earth that we just have terrible resolution in all respects?
No, and depends at what scale you're looking at. You'll see. I'll get into this, but yes, there is always somewhat lower resolution in the southern hemisphere than in the northern hemisphere, but it's not, dramatic or whatever.
I guess
hopeless.
My question is, do you think we could be missing important structures due to a lack of resolution?
Again, it depends at what scale. At the very long wavelengths, I don't think we have a problem. Once you get to shorter wavelengths,
at a fine scale.
Fine scale be more difficult. Okay, so Adam showed these slides, but in the subduction zone, you get now some very, very kind of really beautiful pictures, I think, of what goes on in subduction zone settings. So this is in Japan here, Honshu and northern Bonin, and you can see, you can see clearly. This is 400, 600, and 1,000 kilometers. These lines. You see here the white dots are the earthquake locations. You can see the slab going down and ponding on the 660 kilometer discontinuity. Here you have two slabs, and they kind of interact, I guess, some fashion. This is the more interesting feature in Tonga, where you see similar things, but you see that, in fact, there is in some areas, I guess all of these pictures show this, it appears like the slab is ponding at 1,000 kilometers, more than 600. There's some portion that ponds at 660. And this seems to follow the seismicity, actually, interestingly. If you look at closely, you have some seismicity that branches off here and some that goes down here. So this is, a very intriguing result that in addition to something that might be happening at 660, there might be something happening at 1,000 kilometers. Yes, that's right. This is another picture which is now from Java region, where you have some slabs going different directions, where you also see some evidence for this type of behavior. So this is really interesting.
Barbara?
Yes.
In the geodynamic models, we often have an effect that we kind of get like overshooting in regions of large amplitudes in our models. In the pictures you showed in the last slide, it seemed like below the oceanic slab, below the subducting plate, we often see a low velocity anomaly below the plate, like this region.
Here?
Yeah.
Uh-huh.
Is this something that you
resolved?
Think is real?
Yes,
that is
I think this
something
is
that is trapped below the slab?
I'll show you at the end, if I get there, a comparison with a model that we did on the global scale using completely different data, which actually shows this also. So,
So if we were to overlay on these models the resolution contours, what would we see? I'm sort of asking, could things be going through the 1,000 and we just lose model resolution below
I
that?
think, well, I'm not showing the resolution. I'm not even sure they have them in the paper, but I will. Well, this is always a question, but I think these are really well resolved. I mean, this might be real or not real, right? But the fact that most of the feature is mostly constrained to be above 1,000 kilometers, I think is probably well constrained. I'll show you a comparison with a model which is done in a completely different way and shows the same result.
There's a related question. So whether we could resolve whether the feature keeps going down. The other question is, what's the property of the temperature derivatives of velocity as you go down?
Well,
if we had the same thermal anomaly going all the way down, does it remain just as visible below 1,000 kilometers?
Well, okay, yes. So these are questions, of course.
I'm not saying you have the answer.
Yes, but the fact that this thickens horizontally is definitely well resolved, and this is also what you see in global models from shear wave velocity. I'll show it in a minute. So the fact that you have a narrow zone going down like this, and something much thicker horizontally, much spread out, more spread out horizontally, is also seen from the global models, so from the global shear wave velocity models. So I think there's no question. Now, of course, you can ask, why don't, if you stop seeing something, is it because of the properties of the mineral physics? But that is something maybe the group might address in some way. Yes.
You can ask the question, is this the property of the slab, or is this like a bulk mantle property? Do we see any evidence for this for something at 1,000 kilometers in like plumes or?
Well, I mean, if you let me give a research talk, I can show you some evidence in the upwellings. Yes. Well, if you're not. Okay, so this was for the subduction zone. I think the take-home message is subduction zones are well constrained. There's still some questions. If you want to go to finer and finer scales, you might have other questions about what's the scale that you can resolve. But they are the best places on Earth where we have the highest resolution because simply of the illumination. Okay. Now, if you go to the oceans, things become more difficult. And this is just an example of comparing a global shear wave velocity model here, a recent one, and I'll talk about how it was constructed in a minute, compared with the Princeton shear wave velocity model, just to show that you have to be careful because, look, for example, here, in this particular model, you're seeing a straight line, and that is most likely due to the fact that the measurement is done on an island here, and that's probably Easter Island. And because you don't have those crossing paths, you end up seeing a continuous, very straight feature. There might be something going on, but it might not be as straight as it is imaged here, right? So, and I mean, it's even clearer, you have these streaks, etc. So beware of streaks in models, in P or S models that are using only body waves. In the upper mantle, especially. Yes?
So, just to the west of west of Tonga, there's a rather dramatic red streak in the lower figure.
Yes, that's also an artifact. And you can see this streak here. Right?
So this isn't a real
feature. These are rays
feature.
Coming to stations here from some distant events, okay? And they're not, etc. I mean, the P-wave model shows it even more, right? There's also, I mean, I'm not being completely fair here because there's also a parametrization issue in this model. They have some tetrahedral kind of blocks which kind of emphasize even more this story. But you do have these problems. So,
Barbara?
Yes.
Sorry. So, maybe I can ask the question a different way. What can I believe in that figure?
In the P wave in this figure?
Yeah.
Not much. You can believe that there are slow velocities somewhere, that are causing, the station averages basically are slow here and there's some fast here. But the depth dependence is probably not right. And, I'm showing it, Husnollet will recognize that, especially in the upper mantle, their models are not very well constrained with only P waves or only S waves. Okay. Yeah.
Actually, while you're going to be talking, can you tell us about the partial derivatives?
The partial derivatives do go through lots of changes in the upper 800 kilometers or so, but there's nothing in the mineral physics as we understand it now that shows anything remarkable at 1,000 kilometers. Yeah. What I wanted to ask you in the top figure, in S40 RTS, one of the things that strikes me is that the subducting slab doesn't show up.
Okay, I'll show you a new model that shows it. This has been a challenge in global shear wave tomography, is to actually kind of see the slabs it has been. Okay. So anyway, let me finish. In DW, so why is this a problem? So now we're looking again at this checkerboard pattern, showing that in the southern Pacific here, or in the southern hemisphere, you can't really recover your checkerboard pattern. And even if the checkerboard is not your ultimate test, if you can't recover your checkerboard, you've got a problem, right? So, and this is Montelli et al. At the lowest, it's an average over the lowest 100 kilometers, and the most interesting features happen to be in this region. And I will not say that they're wrong, because in fact, they may be shifted, but there are things going on. We know there are the super plumes there, right, the LLSVPs and stuff, but it is a problem to be using only P waves to do the tomography. So what do we need to improve this? Well, we need seismic stations in the oceans, obviously, right? And these floaters that, I don't know, I know we had a conversation about this with Jessica, I don't know if it was public, that they're putting in the oceans to try and measure P waves as the floaters go, are being moved by ocean currents. That's one possibility. Of course, you'd want some even higher, even better stations on the ocean floor. This has been it's been hard, because I've been working on this for 25 years, and we're still working on it to get stations on the ocean floor, or a decent array of stations on the ocean floor, even temporary or whatever. But that's one thing. But we have another solution in the meantime, that we can improve our models by using a combination of seismic phases. P waves or S waves are not the only thing that we have at our disposal. And you already know that surface waves travel. Of course, they sample only the top part of the mantle, but they travel a long distance from coast to coast, so they will give you some resolution in the oceans, right? So this is basically, if there is one take-home message from all this lecture, it is that you need to use combinations of different seismic waves to really, get at some decent resolution in the mantle at the global scale. So this is a slide from Ritzema et al. 2004, which shows, what can you resolve with different data sets. So this is different depths in the mantle. What happens if you only have, and these are shear waves, if you only have surface waves, fundamental mode surface waves. Fundamental mode surface waves is mostly sensitive to the uppermost mantle, so at 120 kilometers you have good resolution, but you can't say anything about the deeper part of the mantle. But note now, because of the fact that surface waves travel long paths between sources and stations that can be on different continents or on different sides of the oceans, you do get long wavelength resolution of the global structure, okay? Practically equally well in the oceans and in the continents. Now you add overtones, which I showed you the sensitivity kernels, and now you can start having better resolution down to the transition zone. Okay, this is shown in here. You still don't have much, of anything in the lower mantle. And then you need, in fact, travel times of shear waves and other phases to start resolving the lower mantle. And again, this picture contains more than just S waves. It contains multiple waves that multiply reflect on the core mantle boundary, and other phases that will help you get the resolution. I will skip this because doesn't show resolution. No, that doesn't show resolution. That just shows you what waves are sensitive to what and what structure you can get from different types of waves. If you combine them, you will.
It shows what structure is present.
You
can't tell whether there is structure at 1600.
Yes, that's right.
That is not resolved, or there's not there.
No, it's not there. Right. Okay. So you need all of these to start building a whole mantle model. So now we've made, over the years, right, I like to show this slide because this is the first tomographic model of the upper mantle using actually long period waveforms, which shows a global picture at long wavelengths of the structure at a depth of 100 kilometers. At the time, only really long wavelength structure was possible to resolve, but most of the structures that we know today were in place. We saw the slow ridge system and back arcs, the increase of velocities with the age of the plate, the cooling of the plate, the faster than average continents or cratons, right, are there. Today we have made progress in getting these features to be, better resolved in their details. So this is just a comparison. And models built with these combinations of data actually agree quite well. So the next part of my talk was to show that, how well we agree, especially in the upper mantle. So these are 3 models developed by different groups using different data sets. The top and the bottom ones have used a combination of surface waves overtones, normal mode splitting, long period, different types of long period S waves, body waves, S, SS, SCS, SKS, etc. This one was actually built entirely using waveforms, and I will talk about this later. But you can see that to a large extent these models are in quite good agreement up to some level of detail. And I won't show you this because you've seen it. Adam showed this last week. When we go deeper in the mantle, the structure changes. I want to point out, though, that by the time you get to 600 kilometers in these relatively long wavelength models, you see the subduction zones, but you see them wide, quite wide here, not as well visible here. And this is quite in good agreement with what you see with the higher resolution subduction zone models, that you actually have this flattening in the transition zone, which is expressed by the width here, which is resolvable in this type of tomography. And as you go deeper, in these shear wave velocity models, you see most of this disappears. Only some areas, which happen to be the ones where Fukao sees also stuff at 1,000 kilometers, but most of the other signals. And you also know that by the time you get to the bottom of the mantle, the structure has changed very dramatically, and you have these 2 large shear velocity provinces, low shear velocity provinces, surrounded by this ring of fast velocities. And again, to illustrate this, I think Ved showed something similar, or exactly the same, perhaps, in his talk. The different models differ in their details here at 2,800 kilometers. These are 5 different models constructed with different techniques, different data sets, but they all show the same, very similar patterns, not in the details, but these are data. These are bounds, SCS minus S travel times plotted at the bounce point of the SCS being the wave that is reflected on the core mantle boundary. You can see that in the data already, without doing any inversion, you see this pattern. And what Ved did here was to look at how the models agreed between each other. So basically, they classified at each point, a grid point here on the surface of the core mantle boundary at 2,800 kilometers, which models agree that the velocity is slower than average, which agree that they are is faster than average. So blue means that they all think they're faster than average, and red is they all think that they're slower than average. And you can see that the agreement is really, really good. And remarkably, even the borders of these features, except in some areas like here or here, they are in agreement. So you have a fine-scale structure which actually, from these very relatively long wavelength models, that is in agreement. Of course, inside here you have structure that may or may not be in agreement, but on average, they all show this slower versus very contiguous, higher than average velocities, with the exception of this little perm anomaly. The other thing I wanted to show that is from these models, we also know we can compute the spectrum of heterogeneity. So basically, what is the strength of heterogeneity as a function of wavelengths? And so we express this in terms of spherical harmonic degree. The lowest degrees are the longest wavelengths, right? The degree 2 is the longest wavelengths, and then as you go to higher numbers, you see shorter and shorter wavelengths. And this is pretty well constrained now by these global models, that you have a spectrum which is at the surface of the Earth and at the bottom is very strong. You have very strong heterogeneity and kind of towards the longer wavelengths, but concentrated towards the longer wavelengths. In the top, it goes all the way to maybe a degree 10 to 15. At the bottom, it's really dominated by the degree 2. But then in the mid-mantle, you see that you lose this long wavelength structure, and the structure is more finer scale, more white. The spectrum is whiter, which likely reflects the fact that the actual structure there is made up of smaller scale features than in the two boundary layers. And you expect this kind of pattern in a convective cells kind of system. So one more comparison.
There's a lot of degree 1. There's a lot of degree 1 power in the top 400 kilometers. Is that the artifact of hemispherical resolution?
Well, there's a lot of degree 1 in the continent ocean. Yeah.
The Pacific plate versus everything else is about degree 1.
So this is a comparison that Matthias Mechede, who's a graduate student at IPG in Paris, has made recently of recent models to kind of see how well they agree. And so what you have here is 5 of the most recent global shear wave tomographic models, and then compared with some regional models in some regions. So this is here in the South Atlantic. This is in Europe, this is North America, this is Australia, and this is a zoom in on the western part of North America. And the point here is to show that there is really, we start to have really good agreement even at the smaller scales. Some of these models, like S362 ANI, which is the Harvard model, are by design rather smooth, and so they don't see as many details. But some of these most recent models actually see a lot of details here, the ridge structure and the continent, etc., which actually agree quite well with what is seen from regional models, which have been constructed with data, focused on resolving a particular region of the world. And so the point here is that with the global models, we are starting to reach resolutions that are, comparable to what you can do at the regional scale. Just a point here: these are some recent, very regional models, very more local models, and they show the same trends, but the amplitudes are off. And this is kind of a puzzle. Why that is? It's most likely because they do not include the long wavelength structure. Actually, they're missing the long wavelength structure. These are spectra. I think I'll move on because I I won't have time to show what I really want to show. But so this is another way of looking at these, comparing these models, which is the spectrum. This is between 100 and 200 kilometers depth, so it's average structure. Again, in the Fourier domain, if you want, but it's the power per octave, so you don't see. It's power per octave is basically as you multiply each at each degree, you multiply the corresponding power by L, so you kind of bring down the long wavelengths and have a better view of the shorter wavelengths. But you can see that these global models agree extremely well all the way to degree 16, perhaps. Some of them even higher in even small details of the spectrum, and then they fall off. S40RTS has a problem here. There must be a regularization problem here at short wavelengths, but the other models have pretty much the same trend. And if you compare them with some of the most recent regional models that have been constructed with kind of modern techniques, waveform-based techniques, you can actually continue the spectrum, the trend of the spectrum to higher, to even shorter wavelengths quite continuously from the global to the regional models. But anyway, okay, so let's, how do we gain higher resolution? I mean, this is really what we want, given all the limitations. So we can improve sampling, of course, by introducing other phases, right? More seismic phases, more information, more waves that bounce around the mantle to give you an illumination, a better illumination since we lack a uniform distribution of sources and stations. And yes, in order to do this, we have a whole alphabet soup of phases. This is a travel time curve with all the body wave phases here indicated. But you notice that it becomes difficult to measure specific phases at some point because they come too close together to each other. So you can't really measure the travel time very well because they're interfering with other phases. So the answer to this is to, instead of using waves, just the waves that are well separated in the seismogram where you can really measure the travel time, use waveforms. Use the whole seismogram, right, which will contain all of these waves, and therefore you'll have access to more information in there. And then, so that's one way. And in parallel, you also need to, once you get into waveform, you need to improve the wave propagation theory because you can't just relate the waveforms to a theoretical model by using only the infinite frequency approximation, which is ray theory. Okay, so you have to include the fact that waves have actually represent a combination of frequencies, so it's called finite frequency effects, and these turn out to be very important for resolving slow anomalies. Okay, so what are finite frequency effects? This is I borrowed this from Ved. He gave me this slide showing that, in fact, when you have a wave propagating between a source and a receiver, it's not just sensitive to the infinitesimal path, but it's sensitive to a broader kind of region depending on its frequency. If it's longer period, it's going to be sensitive to a wider band around. And this brings up the question of how do we resolve slow velocity anomalies, and I'll do this. I prefer to do this by hand waving than by showing anything because I haven't found the right slide to show this. But if you have a slow anomaly and you have waves going through it, if you're only measuring the infinite frequency, if you're in the infinite frequency approximation, the ray theoretical approximation, if you go right through the anomaly, you're going to see a slow velocity anomaly, right? You're going to see a travel time that's going to be delayed by this passage through this anomaly. But if your wave is actually sensitive to, but in fact what happens is that the first arriving wave may actually go around the anomaly, right? Because it's faster. So depending on the shape, etc., your first arriving wave, what you're going to be measuring is not the slow anomaly, but the wave that has gone around it, right? So the slow anomaly is hidden. And also, if you have frequency-dependent waves, right? If you have waves that are sensitive not only to the anomaly but also to its surrounding, you actually will observe a travel time anomaly that will be less than what it would be if you were in the high-frequency approximation. So these are all issues that turn out to be very important if you want to get higher resolution and especially map the low-velocity anomalies. Okay. So I think I will skip this. So anyway, the way forward is to do full waveform tomography with the appropriate theoretical approximation of theoretical theory, right? If possible, exact. And that wasn't possible for many years. We still needed to use approximate wave propagation theory. But recently, we have these numerical methods based essentially on the spectral element method, which has been very powerful, which allows us to compute synthetic seismogram, which are very accurately represent whatever structure you have in your model, right? Very accurately. You're not making any approximations. You're not hiding things behind, ray theory or whatever. You really have the synthetic is really a very accurate representation of your wave field that is created by your model in which you are computing your and then you can from the point of view of waveform tomography, you can separate your seismogram into different kind of time intervals, which will contain different arrivals of energy, which may or may not be associated with particular phases, from which you can compute the travel time. They can be mixtures of phases, but by using the waveforms, you don't have to worry about this anymore. There are other issues that show up, of course, when you do when you use the full waveforms and compare the observed waveforms with the synthetics that you compute in your model. One of which is that, especially now that we have access to the numerical methods, this is very time-consuming exercise. Okay, so I'll skip this. I'll skip this. If you want to ask me on the effects on the waves of slow anomalies, you can ask me later. But just to show, so now I'm going to just show some examples of recent work that actually incorporates both the idea of waveform tomography and the idea of using these very accurate theoretical forward computations to basically compare it to the observations. So this is a comparison between this model that Ved Lekits developed. This is the first model of the upper mantle that was developed using this kind of approach. As he can tell you yourself, it's not trivial. It took him 5 years to build it. And because heroically, we had decided that we would start with a 1D model and build it up from 1D, which is basically very nonlinear. The reason for doing this, I was the culprit, is that I thought, since we're building a model using a different theoretical approach, we'd better not incorporate any a priori knowledge about the structure to see if we get the same that we would get, using the standard, more approximate methods. And that's added to the length of because you had to do many iterations to bring in more and more data into the process. Because in particular, the problem with waveform tomography, is that in order to be able to match these theoretical seismogram with the observed seismogram, you have to be relatively in phase, right? The two have to be relatively in phase. If your structure is too far away from the real structure, you may have a very big phase mismatch. Your wave could be, your theoretical wave could be somewhere here, right? And therefore, comparing the two just doesn't make sense. So you already have to be very close enough to within half a wavelength to be able to make sense of a comparison between observed and a synthetic. So you have to build it up slowly, at first you reject most of the data, and as your model becomes more and more 3D, you can include more and more data. So the point here is, okay, so these models look at first view quite similar. The main difference, so that was a good kind of good news, right? Because actually it's good news because it means 30 years of tomography, actually made sense, right? Even with approximate methods. The main difference is really here in the amplitudes of the lateral heterogeneity at the top level, where now, because we can relax, well, at least that's because we have more sensitivity to low velocities, and because we can relax the the damping in the inversion, because our equations are more consistent, we can have better access to the amplitudes of lateral variations. Okay, so, and this is an example, from the East Pacific rise, where we can now, you ask, when do we know that our structure is correct? Well, here we have one area of the East Pacific rise which has actually been directly, there was an OBS experiment from Foresight, that Foresight group that put some OBSs here and was able to kind of derive a model of the local structure here in the East Pacific rise. And so this is the model here, right? This is as a function of depth, shear velocity here. This is this model of Harmon et al., the mean for that small region in the East Pacific rise. And this is in comparison two recent models, the S362 ANI and S40RTS. You can see the general trend is there, but the amplitude, the absolute velocity anomaly is much weaker, right, in the global model, right? So, that's another take-home message from looking at these global maps. You can believe the patterns. The patterns are well constrained, but the amplitude of the lateral variations may or may not be very well constrained because of all the damping and all of the stuff that goes into the inversion. So you have to be careful when you want to interpret a model in terms of its meaning, in terms of mineral physics, etc., that you can't necessarily, trust the absolute velocities. But anyway, so that's one of the things we are striving for, is getting better constraints on the absolute velocities. And now, with this new model, right, which is with a somewhat improved, theoretical. This is actually the second generation, which was built by Scott French. And you can see we can match, without trying, right, because this was completely independent, we can match the low velocity minimum much better in this area. Okay, and so this gives us confidence that our velocity at this scale, at the scale at which we are working here, the velocity structure is pretty good, and we can then have more confidence that if we now expand along the East Pacific rise, right? So now we're going beyond the region that has been sampled by the experiment. That the structure that we get of the low velocity along the East Pacific rise is well constrained, or better constrained, right? Both in velocity and also in its depth distribution. This is the velocity. This is the answer. So I guess I have to stop here, but I'll show one more. Yeah.
So you're basically talking about, if you go back, the one before that, if you do like if you use the ocean bottom seismometers, you get a slightly different value for the amplitude of your velocity anomaly.
It's not slight. It's
or it's a large. So my question is, how if you're looking at like the core mantle boundary or something, or deep in the Earth, how large is your uncertainty?
Okay, so this is the upper mantle. We're working on the lower mantle right now. Okay, the uncertainty will likely be larger. Again, it depends on the scale at which you're looking. If you're looking at degree 2, we have very good agreement. But degree 2, whether degree 2 can be translated directly into a mineral composition is the issue, right? It's not.
Well, these people are talking about heterogeneity. You're trying to think of. I really want to know how large that uncertainty. What my error bars are, right?
you have to discuss it in terms of at what scale.
At finer scales, we're talking about, let's say, like UL, like really tiny features.
Okay, so ULVZs you do not resolve with global tomography.
Yeah.
ULVZs you have to use very specific target experiments where you actually do more like forward modeling.
Like the large
yes.
And like this, in one of them it looks like it's a large blob, and the other one has finer scale structure.
So.
Yes. Okay.
Maybe the takeaway message from this is that if you use correct theory and full waveforms, that your uncertainty decreases substantially, so that when you're faced with the choice of which tomographic model should you try to interpret, you choose the ones that are constructed with more sophisticated methods.
Okay, so the final slide, just to answer the question that was asked about the subduction zones. This is a comparison. This model is actually not published yet, but this is Scott French's model of the whole mantle, right? So, we went from upper mantle 2 generations with details that I didn't even get into, and then now whole mantle. And these are cross sections from the Fukao and Obayashi model, right? With the slab going, some of them ponding at 660 and some of them ponding at 1,000. And this is from this new model that is, just constructed recently with the full waveforms and the spectral element method. And you can see that we're starting to resolve the subduction zones, right? I mean, I think this is the message. Now you can kind of quibble as to whether this is more right than this. Okay, and this is something we should be looking into, but it's quite encouraging that we are starting to get the resolution at this scale from the global. And then finally, I'll show you this, and if you want to hear more about it, invite me to give a research talk. Yes.
Yes. Well, for the recording. So Barbara, I think that's really encouraging, that matching of the OBS experiment of the amplitudes, because to do dynamics, we need to know the amplitudes, right? And the damping in tomography has always been an issue for, true interpretation, especially if you want to match geology. Right. So
we're getting better, right?
We?
Well, so we're getting close, but again, it's a scale-dependent thing, right? Because you have to think about it. This is average over some wavelength, right? We still have a limited resolution. We're not seeing at the microscopic scale that you would really want to if you really wanted to do things. So you have to take that into account when you interpret a model. Is what is the lateral resolution that it has, so that you have to then put your data that you want to compare it to, geodynamics or mineral physics, through the same kind of filter, because that will reduce your amplitude, right? And I think that's an important point, because I'm not sure people are aware of this that much when they do this comparison of models with mineral physics and whatever. Not always, anyway. Yes.
So in the plots of the spectral power that you showed, where there was essentially not much going on in the mid-mantle, is that then, earlier you sort of indicated that the mid-mantle has, in all these different methods, the least resolution. Is that really that combination of...
Okay, so yes, the resolution is not as good in the mid-mantle, but the structure is also finer scale, if you see what I mean. If there was strong degree 2 or degree 2 to degree 5, we would see it. I mean, our resolution, even if it's lower, we would see it. The fact that we don't see it means it's not there, it's there, but it's at a relatively lower level because the spectrum is pushed to the higher degrees. So it does mean that the structure is smaller scale, right? It's dominated by smaller scales, but then we can say that, but whether we can resolve that smaller scale structure is a problem, because our resolution is not as good, right? So, but that's, and in this work that Matthias Mechede has been doing, we've been kind of arguing, because he claims that what those models are showing are all noise, actually, in this depth range, and I would not be that pessimistic. I think we see, we are starting to resolve some structures, but they're definitely harder to resolve.
I have a question about the second to last slide with the subduction zones. If you can go back.
Which one? The subduction
one
zones?
after this, I think. That one.
This one? Yes.
So on the left, under the 1,000 kilometer thing, you can see some blue structures going down to the core. Would you consider that part of the slab that has been?
Okay, so I think this model here probably has lower resolution at the core mantle boundary than our models. That would be my guess, but I'm just putting it out without.
So it could be the slab or not, but we don't know.
Just because I know what waves they used, so they have more, because of the kind of illuminations they have, they probably, are losing resolution at the core mantle boundary. They don't have diffracted waves, I think.
Okay, because one thing for the group is whether or not something changes in the slab where we can't see it after the 1,000 kilometers. So I was wondering if
Sorry, I can't hear you.
So one idea for the group of what happens to slabs at 1,000 kilometers, that something changes in the properties where we can't see the slab after that depth.
Yes, well, that's possible. I mean, in this range, yes, I was sort of focusing on this blob.
Okay.
Because the models are different, we should look at some other models too, right, to see what happens here. This is just the latest Berkeley model, right? And but in the middle here, yes, this is a really big question. Okay. Why don't we see them?
Okay. It doesn't have to be the same slab either. They don't need to be.
No, of course, yes. No, they don't need to be contiguous. I mean, on average, it's blue, right? It's bluer, but very, very faint. So. Okay, I think everybody's hungry, so.